Geometry, Unit 6, Section 2, the ratio method. The previous video was on scale drawings, and so we saw our first constructions on how to create like a dilated figure, a scale image of twice the size or half the size or 3 times the size. And really the ratio method is another way of doing that, but the center of the dilation is not necessarily on the figure. So like in the scale drawings that we saw, let me just flip back to the previous slides. We kept angle A and I just extended these, and we could cut sides in half and stuff like that. But what we're seeing here is I want to create a scale drawing but centered at this point O. And so I'm going to get a completely different triangle over here. And so you're going to see kind of like it expanding out from O. And that's a good way to think about it. So to create a scale drawing of the figure below using the ratio method about center O, the scale factor R equals 2. So this one wants a ratio of 2, so we want twice the size. I want to make a triangle ABC, A prime, B prime, C prime, and I want to make it twice the size using center O. So the first thing that we do is we use our line tool and we draw lines from O to each of our points, but extend it well beyond, more than twice the distance. The reason why I'm doing more than twice the distance is because my ratio is 2. So more than twice the distance. And so I just draw these lines out. And then it's very similar to how we did our scaled images. It's still a scale image. That instead of measuring the length of AB and doing twice that, I'm going to measure the distance from each point to the center of the dilation here, O. So measure the distance from O to B. And my next point is going to be twice the distance. So then I double the distance. And that's what we do for each of our points, because what this will do is if B prime's twice as far, that's going to make sure that my lengths are twice as long, because my ratio is 2. That's what I'm going for. So that's how we do this. So it's actually really not too complicated, not too bad. And so then I just, remember, you always got to make a slash for the measurement, and then we go to the slash and make our next point. And you try to be as precise as you can. You could probably be even more accurate than I can with the smartboard. It has its limitations. All right, and then right there. Okay, so now I'm going to make points at these locations, and I'll label them. This is B prime, the image of B after a dilation of 2, and A prime, the image of A after a dilation of 2, and C prime. And so all that's left for me to do is to connect my points. And we will see a figure, an image of our original triangle twice the size. And so now if I were to take my ruler, I could measure the length of AB and then A prime, B prime, and I see that it is twice the size. But again, the way that we did this was not by doubling the length of AB like we did in the previous, but by doubling the distance from the center we're using for the scale. And so that's how you do that. All right, we could go the same thing, but we can make things smaller. Like here in this case, I have, these are 2 separate questions. They're just kind of on top of each other. But I didn't need a whole second page, so I kind of did this here. But so just ignore this stuff for now. Just look over here. So create a scale drawing of the figure. So line ED, I want to make it half the size with center O. So what we did up here was first thing we did was we drew these lines from the center to the point. And I went beyond that, more than double that, because my ratio was going to be 2. Well, I'm still going to connect these lines, but I don't need to go further out because my ratio is making things smaller. So I could just, connect them, and I'm going to find what's halfway through. You can go a little bit, but there's no point in drawing these lines out here. I'm not making ED larger. I'm making ED smaller with my ratio of 1/2. We know when our ratio is less than 1, that makes an image that's smaller. And so instead of halving the length of ED, I'm going to half the distances of each point to O. And we know the way we can half a distance is with our perpendicular bisector construction. So that's what we'll do here. And we know for a perpendicular bisector, probably, no, I wouldn't even say probably, it is the most important construction of our course because we use it in so many applications. Okay, so flip that. I can use it to find a midpoint, to bisect something like we're doing now. And let me do this line in blue. Okay, so right here I found the image of what's going to be known as D prime, because this is the length of OD. Well, I found the length of OD prime, so it's going to be half the length because I found the midpoint of that line segment. All right, and we'll do the same thing over here. And let me just change my color. And flip. And this time I'll do a green line to match my arcs. And that location, that whole construction is just to find this point, which is E prime. So now we can connect these points and this here. Let me just change that back to black. This here, this E prime, D prime, is half the length of ED. But not just half the length, it is also parallel. And the same thing for all these, that AB and the prime image here, yes, it's double the size, but it's parallel to the original. Same thing with the BC and its prime, twice the length, parallel to the image. AC, twice the length, and parallel. The angles are still congruent. Corresponding angles are congruent, but the sides have changed in a proportionate manner. All right, the last thing, well, what if they give you two dilated images like this, a scale drawing here, that figure B is a scale drawing of A. It doesn't really matter, or I could say A is a figure of B. It's almost like, well, B is half of A, or A is double B, either way, right? How do I find the center of the dilation? Well, again, take a look at how this image was, that connecting all of these points, they all come down to the center of the scale, the center of the dilation. So all we have to do is take a couple of corresponding points, like, let me highlight them a little bit here, that this point corresponds to this point between the two figures. So just draw a line connecting those. And what else? Just pick another pair of points. Let's say this point corresponds to this point. And so draw a line connecting those. Where they cross, that's the center of the dilation right here. And we can label it O. It tells us to center O. And I could do any other any two other corresponding. They will all land in the same spot. All right, so they will land in the same spot. They will land in the same spot because it's all coming from the same point. That's how it was created. So finding the center is just connecting a couple of lines. That's not too bad. Doing expanding with the ratio method, just extend the lines out and then find the distance from each point to the center and double it, triple it, whatever the ratio is. Or maybe you're halving the distance. And finding the center is really not too bad. So very similar to the constructions we saw in the previous video. All right, that's it for now. Our next one is going to be discussing what we call the side splitter theorem. We'll save that for the next video. See ya.